Hey guys, welcome back to another round of chemistry notes. In this video, we are going to talk about bonding. So a chemical bond, or chemical bonds, are the attractive forces that hold groups of atoms together. They are caused by electrons, and the goal behind bonding is for each atom to have 8 electrons in its valence level. Like we learned in Unit 5, this can be achieved a couple of different ways. It can be achieved by losing electrons, or by gaining electrons, or by sharing electrons. In any case, the goal is always to end up with 8 valence electrons, and this is called the octet rule. And if done correctly, every atom in the bond will achieve the lowest possible energy state. What this means is that it's going to be the most stable. The idea behind bonding is to make everything more stable. So our first type of bond we're going to talk about is an ionic bond. This is between a metal and a nonmetal. This occurs between elements with very different electronegativities. Remember that electronegativity is how strongly an atom, a nucleus, can pull on electrons. So if you've got two very different electronegativities, two very different strengths or pulls on electrons, you are going to get a transfer of electrons. The valence electrons of one atom will just straight up move to a different atom. One will lose, another will gain. The particles of ionic bonds are called formula units. Remember, that's the smallest representative particle of an ionic bond. And the reason that a bond forms when electrons are transferred is that elements that lose electrons, remember those are your metals lose electrons, they're going to be attracted to the elements that gain the electrons. Remember, nonmetals will gain electrons. So then you end up with a positive metal ion and a negative nonmetal ion, and as we learned in our last unit, opposites attract. Your positive metal will be attracted to your negative nonmetal, and they will form an ionic bond. So that is sort of a review of what we learned in Unit 5. What we didn't really talk about in Unit 5 are properties of our different types of bonds. So ionic bonds, when they form, will reduce the potential energy. They will become more stable. And this part, the become more stable part, this is not unique to ionic bonds. This is true of any bond becomes more stable, but ionic bonds do this by arranging in what is called a crystal lattice. It's just a very structured arrangement, and it looks like a crystal. Remember, sodium chloride, table salt, is an ionic compound, and if you've ever, just stared at salt, it has a kind of crystal structure. It's a very regular shape. That's the crystal lattice, and it makes it more stable. Your ionic compounds have relatively high, melting and boiling points. They are hard. They are brittle. And they will conduct electricity when they are dissolved in water. Put another way, they're electrolytes. Probably heard about electrolytes in, Gatorade commercials. An electrolyte is just something that conducts electricity when it's dissolved in water. Any salt, any ionic compound is an electrolyte. You are going to need to be able to draw the Lewis structures for ionic compounds. So remember, we learned about Lewis structures a while back. We learned that you draw the symbol of an element and then draw a dot for every valence electron. Well, now instead of just drawing individual atoms, we are going to draw ionic compounds, an entire compound. So, two things to remember when you're doing this. Metal ions, when you draw the ion instead of just the atom, metal ions are always naked. And nonmetal ions, again, not the atom, but the ion, are always stuffed. It sounds a little silly, but here's what that means. So we're going to draw metal atoms, and then we're going to draw the metal cation that it forms. And metals, when they form ions, will be naked. These will be naked over here. And nonmetals, when they form anions, they will be stuffed. Remember, anion is a negative ion. It has a negative charge because it has gained electrons. Cations, right? Cations are positive. They have a positive charge because they lose electrons. So lithium, which I actually drew on the last slide, here's lithium. It's Li. It has a single valent electron. That's the atom. This is neutral. When it forms a cation, it's going to lose one electron. Remember that lithium is an alkali metal, and all alkali metals will lose one electron, specifically this one electron. So the lithium cation will be the symbol for lithium, but instead of now having a dot for the valence electron, it'll have a +1 charge. Remember, you lose one electron, you get a +1 charge. Taking a look at aluminum. If you find aluminum on your table, it's in the third group, which means it has 1, 2, 3 valence electrons. But when it forms an ion, when it forms the aluminum cation, it will lose 3 electrons. It has 3 valence electrons, it will lose 3 valence electrons, and it will form the aluminum ion, which is the symbol for aluminum, but now it's naked. All of its valence electrons are gone, and instead it has a 3+ charge. Lose 3 electrons, form a 3+ charge. So that's how you draw your metal cations. Pretty straightforward. They lose their valence electrons, they form a positive charge. On the other hand, we have our nonmetals. So the nonmetal fluorine, the atom is the symbol for fluorine, which is F, and 7 valence electrons. If you find it on the table, you'll see it's in the 7th group. It has 7 valence electrons. So when it forms an ion, the easiest way to get those full valence electrons is to gain 1 electron. So it'll be fluorine, and it'll have the 7 electrons it started with. But now we have gained 1 more electron. And now we have 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8. It is stuffed. That's why we say that they are stuffed. They are holding the full 8 valence electrons. That's all they can possibly hold. So to show that this is now an ion, because we've been messing with the number of electrons, we will put this in square brackets and give it a charge. We gained 1 electron, so we have a -1 charge, or just a negative charge. We can do the same for phosphorus. So we'll draw our symbol for phosphorus, which is P, and then we will draw our 1, 2, 3, 4, 5 valence electrons. When phosphorus forms an anion, it will gain 3. It has room for 1, 2, 3 more electrons. So phosphorus will gain 3 electrons in order to be stuffed. So then we will have phosphorus, which is P, with 1, 2, 3, 4, 5 that it started with, plus an additional 1, 2, 3 electrons. And now it has 1, 2, 3, 4, 5, 6, 7, 8 total electrons. It is stuffed. It has a full valence level. It is happy. So then we can put it in those square brackets and show the charge. Since we gained 1, 2, 3 electrons, we are going to have a 3 negative charge. Now this is how we talk about ions forming, but we've sort of glossed over something here. you can't get rid of electrons. You can't just destroy electrons. We didn't just delete this electron right here from lithium. We didn't just delete these 3 from aluminum. You also can't create electrons. We didn't just pull this electron out of thin air. We didn't just create these 3 electrons here. What is happening is electrons are being transferred. This 1 electron that we are losing is coming over here to fill in for fluorine. This electron is being transferred from lithium to fluorine. Same thing here. Aluminum loses 1, 2, 3 electrons. Fluorine has gained 1, 2, 3 electrons. So they're not being deleted and then created. They are being transferred from our metal to our nonmetal until everyone has the correct number of valence electrons, until everyone is happy. So that's what we're going to look at next, is how to actually put this process together to draw actual formula units of our different ions together. So this is what it says in your notes. We're going to alter this just a little bit, simplify it a little bit, but we can start with the first step is going to be the same. To draw the Lewis structure for a binary ionic compound. Remember, a binary ionic compound means it's made of 2 elements. So this is not going to include any of your polyatomic ions. This is just a metal ion and a nonmetal ion. The first thing you're going to need is to determine the formula of the compound. Because remember that the formula is like the recipe. It tells you how many metal ions and how many nonmetal ions you need. So then once you've determined the formula of the compound, draw the structure of each ion. And that's it. That's really all you have to do. You can check yourself by drawing. So these are what you actually need to do. This is sort of a check, make sure you've done it correctly. If you have drawn the right number of cations and the right number of anions, then you will have exactly the right number of electrons that you can transfer electrons from the metal or metals to the nonmetals. If you've drawn something that loses 9 electrons but gains 6, that doesn't work out correctly. So you can use this to double check yourself, but you don't need to necessarily take it into account to draw them. Easiest way to draw your ionic structures, figure out the formula, and then draw your cations and your anions. So let's take a look at this. So our first example here is calcium oxide. First thing we need to do is figure out the formula. So remember that calcium is a Ca2+, and oxide is O2-. So we get 2 positives from calcium, 2 negatives from oxygen, means that the formula is just going to be CaO. We need 1 calcium and 1 oxygen. So we can go ahead and draw our ions. Calcium is a metal, Ca, so it's going to be naked. It won't have any dots. It won't have any electrons. And then its charge will be a 2+. Oxygen is a nonmetal, which means it should be stuffed. So we will start with the symbol for oxygen, which is O, and then we will give it a full 8 valence electrons. And then to show that we've altered the number of electrons, I didn't leave enough space here, we'll draw our square brackets and give it that 2- charge. So this is the Lewis dot structure for calcium oxide. If we needed to prove this to ourselves, we could say, well, calcium starts out as Ca with 2 valence electrons. And then oxygen starts out with an O, and then 1, 2, 3, 4, 5, 6 valence electrons. So we'll have 1 electron from calcium transferred to right here, and then we'll have this electron from calcium transferred to right here. We'll end up with a naked calcium ion and a stuffed oxygen ion because we lost 2 from calcium and gained 2 in oxygen. So sort of double check yourself there. We are all set. Let's move on to the next one. Letter B here is aluminum sulfide. So again, we know that aluminum is Al3+. We know that sulfide is S2-. So then to make our positives and our negatives cancel, we are going to need 2 aluminums and 3 sulfides to give us a formula of Al2S3. So then to draw this, we'll need to draw 2 aluminum ions, and they will both be naked. So we'll draw Al with a 3+ charge over here, Al with a 3+ charge over here. Then we'll need 3 sulfide ions. So we'll have a sulfide ion, which remember it's a nonmetal, so it should be stuffed. It should have 1, 2, 3, 4, 5, 6, 7, 8. Give it brackets and a charge. So that is 1. We'll draw another one down here. 1, 2, 3, 4, 5, 6, 7, 8. Brackets and a charge. Then we'll draw one more. 1, 2, 3, 4, 5, 6, 7, 8 with brackets and a charge. So now we've got our 2, 4, 6 negatives and our 3, 6 positives, our 2 aluminums, 3 sulfides, everything works out. If we wanted to just prove this to ourselves, again, we could draw the initial atoms over here. So we start with 2 aluminums, Al, and they each have 1, 2, 3 valence electrons. Second aluminum, 1, 2, 3. And then we'll draw our sulfides, sulfurs over here. Sulfur with its 1, 2, 3, 4, 5, 6. Another sulfur, 1, 2, 3, 4, 5, 6. And another sulfur, 1, 2, 3, 4, 5, 6. So now we're going to have to transfer electrons. Good thing we've got 1, 2, 3, 4, 5, 6 over on our 2 aluminums, and we are missing 1, 2, 3, 4, 5, and 6 over here. So we will just transfer the 6 electrons from aluminum over to sulfur. It's not pretty, and you do not have to show this, but hopefully this at least helps you see a little bit what's happening with the electrons and what we mean when we say transfer from aluminum to sulfur. From the metal, they are given to the nonmetal. And again, this is because your nonmetals are very electronegative. They're really good at pulling on those electrons, versus your metals are not very electronegative. They are not good at keeping those electrons. All right, 2 more examples here, and then you'll have some to practice on your own. Our next one is magnesium fluoride. So remember that magnesium is Mg, 2+, fluoride is F, 1-. So then our formula is going to be Mg, F2, meaning that we are going to have 1 magnesium atom to start with its 2 valence electrons, and we will have 2 fluorine atoms to start with. F, 1, 2, 3, 4, 5, 6, 7, and then F, 1, 2, 3, 4, 5, 6, 7. But again, this magnesium has 2 electrons it's trying to get rid of. Means that when we are done, we will have the same magnesium, but it'll be naked now because it's an ion. So Mg 2+. And we will have these same 2 fluorines, but they will be stuffed now. 1, 2, 3, 4, 5, 6, 7, and now 8 electrons. So we'll give it brackets and a charge. And then another one, F, 1, 2, 3, 4, 5, 6, 7, 8. Give it brackets and a charge. Remember, the charge always goes to the top right. So this magnesium gave 1 electron right here and 1 electron right here. So magnesium is now naked and both of our fluorines are stuffed. And last but not least, lithium oxide. So lithium is Li with 1 valence electron, and oxygen is an O with 6 valence electrons. So lithium will give up its one valence electron to oxygen, but then oxygen only has 7 electrons. So that means we're going to need a second lithium to fill in the other electron that oxygen needs. So that means that our formula is going to be Li, we needed 2 of those. O, we needed 1 of those, which again, following our old technique, we have Li with a 1 plus charge, we have O with a 2 minus charge, we need 2 lithiums and 1 oxygen. So we actually kind of learned the shortcut before we learned the real thing. This, what we learned in Unit 5, is a shortcut version of this. And yes, there is even a shortcut to this. If you see it, awesome. If you don't worry about it. But what we've been doing this whole time is the shorthand version of this. The reason that we need 2 lithiums and 1 oxygen is because oxygen has to gain 2 more valence electrons, and lithium only has 1 to give, so we're going to need 2 of them. So all of this sort of comes together to tell us for absolute certain that yes, we need 2 lithiums and 1 oxygen to make this work. So we can draw this over here. Lithium, when it's an ion, this lithium will lose that 1 valence electron to be naked with a +1 charge. This lithium loses this electron to, again, be naked with a +1 charge. Then we have our single oxygen over here. That's oxygen with the 8 valence electrons it started with, plus the 2 that it just gained from lithium. And since it has gained 2 electrons, it has a 2 minus charge. So this is your Lewis dot structure here. Another way to write this is to say that we have 2 Li pluses and an O2 minus. This is not a good way to write your answer, but please know that it is one way this can be represented. If you see 2 Li plus, it means that there are 2 Li pluses. All right, so next in your book, you've got a little bit of practice. Go ahead, pause the video, work through the practice, see if you can come up with the formulas and dot structures of the next 4 problems. And when you're ready to check your answers, go ahead and go over to my website to check the key. It's a little hard to put these into a PowerPoint slide, so go check the key on my website, make sure you've done it correctly. If you have, then you can move on and talk about the next type of bonding. All right, our next type of bonding is metallic bonding, metallic bonds. These are a little different than ionic bonds. These result from the attraction between metal nuclei, so the nucleus of many metal atoms, and the surrounding sea of electrons. So this is a vocab term, a sea of electrons. You need to know this. It is specific to metallic bonds. It is what causes metallic bonds and all the weird properties of metals. In metals, your valence electrons are delocalized and mobile. Delocalized meaning that they don't really belong to any one nucleus. They kind of belong to every nucleus. And mobile meaning that they are free to move around. And think for a second about why metals might have a sea of electrons, some delocalized electrons, versus nonmetals which do not do this. Think on it. Really think about your properties. Did you get there? Metals are not very electronegative at all, right? They have really low electronegativities. They have really low ionization energies. They don't really care to hold on to their electrons all that well. We just saw that in the last type of bonding. Ionic bonds, the metals are giving up their electrons to the nonmetals. So when you just have a whole lot of metal atoms together, no one atom is really holding on to its valence electrons that well. So they're free to just kind of travel around between all the different atoms. So then as an electron gets up and leaves a metal atom, that atom ceases to be an atom and instead becomes a positively charged cation. So this is kind of what it looks like. you end up with electrons leaving atoms so that you end up with an ion, right? We're missing some electrons. You end up with a metal ion that stays kind of in one place. It's in a fixed position. And then your electrons are delocalized and mobile. They move freely. So you've got this electron belongs to this one for just a second, then it'll sort of travel over here, and now it kind of belongs to this nucleus, and then maybe it comes down here. It's free to just flow around between all the different nuclei, never stopping, always moving. So that's what it means by delocalized, is that at no point does it say, this is my nucleus and I'm going to stay right here forever. We're partners now. It doesn't happen like that. The electrons never stop going. And that's why it's called the sea of electrons. They are always flowing, moving around between your different nuclei, right? Even on a still day, the sea is always flowing. These electrons are always flowing between your different nuclei. And this is what causes our special properties of metals that we learned about way back in Unit 1. So the mobile nature of the sea of electrons causes metals to be highly conductive of heat and electricity, and also very lustrous, very shiny, right? Metals are shiny. So the conductive part is pretty cool. Remember that heat is kinetic energy. We've talked about that earlier this year. So you have maybe an electron over here with a lot of kinetic energy. It's got a lot of heat. Because it's delocalized, it can take its kinetic energy all the way down here, and then over here pretty quickly. That heat can flow through here. That energy travels with that electron. So it conducts really well. And then electricity is actually the flow of electrons. So metals, the electrons are free to flow. That electricity is able to move through the metal. So those are some properties caused by the mobile nature of the sea of electrons. Again, this term, you need to know this term, sea of electrons. Also, the ability of metal atoms to move past each other, slide past each other, leads to two other vocab words that we learned in Unit 1, malleability which is the ability of a substance to be hammered into thin sheets, to be molded like Play-Doh. That is malleability. And also it leads to ductility, which is the ability to be drawn or pulled into a wire. All right, so some examples here. It says, explain the following in terms of structure and or bonding. And then A is solid K, solid potassium conducts a strong electric current, whereas solid KNO3, potassium nitrate, does not. Well, the key here is that these are two different types of bonds. Solid K, solid potassium, this is a metal. KNO3, this is a metal. This is a polyatomic ion, so this is an ionic compound. So our solid metal has those special properties that all metals have, such as the ability to conduct an electric current. So your metal has a sea of electrons. K is a metal with a, without using our complete sentences here, mobile sea of electrons. This allows for conduction of electricity and heat. Versus KNO3 is ionic, so electrons are transferred to our nonmetal, or in this case, our NO3. They're transferred to the anion, and then they stay there. If your electrons cannot move, they cannot conduct anything. All right, our next one, which of the following solids will conduct, this should be N, not and, will conduct an electric current? Mg, magnesium, or NaCl, sodium chloride, or CO2. Well, the only things that conduct electric currents in their solid forms Remember, if this were dissolved in water, it would be a different story, but this is in its solid form, will conduct a current that's only going to be metals. So that'll be magnesium, right? Because this is ionic. If this sodium chloride were dissolved in water, it would conduct, but it's not, so it doesn't. So this is covalent, and as we'll see in just a second, there's really not a whole lot that will make your covalent compounds ever conduct current. So magnesium will be able to conduct an electric current because it is a metal. Do a little more shorthand here. And since it's a metal, it has that mobile C of electrons that allows it to conduct. And last but not least, compare the effective core charges of metals and nonmetals. How do the effective core charges of metals lend to the highly conductive nature of these elements? So we talked about this a little while ago in this video. Metals have a low effective core charge. Remember that the abbreviation for that is ZEF, right? This is core charge and then effective core charge. So metals have a very low ZEF, which means they have less pull. ZEF is the pull, it's how well your nucleus pulls on electrons. So we have less pull on electrons, so the electrons can move freely. If you want to see the answers written out in like slightly better English, you can check the key on my website. It really says pretty much the same stuff. All right, so those are your metals. At this point, we've talked about ionics, we talked about metals. Told you there were 3 types of bonds, which means we have one more to go, and that is covalent bonding. So ionic is metal and nonmetal. Metallic is just metal, which means covalent must be just nonmetal, specifically nonmetal and nonmetal. And as we learned in the last unit, for covalent bonds, electrons are shared to fill the valence levels of both atoms that are participating in the bond. In order for this to happen, a couple of things have to be true. Both of the atoms involved need to have similar electronegativities. If one atom is a lot stronger than the other with a much higher electronegativity, it's just going to steal the electrons and it will become ionic. They've got to be really similar. Bonding is sort of like a game of tug of war. Ionic is one person is way, way stronger than the other. One atom is way stronger than the other and just rips the electrons away. Covalent bonds, they may not be exactly the same strength, but they're pretty close. So those electrons stay right in the middle. They've got to have similar electronegativities. They've got to have high ZEF values, which is why this only works for nonmetals. If they had low ZEFs, then instead of sharing the electrons between 2 atoms, the electrons would just float around like they do for metals. And you need to have pretty large radii. Again, if you think back to your periodic trends, these are 3 things that are true of nonmetals. So this is why nonmetals are good at covalent bonding. And remember that particles formed by covalent bonds are called molecules. Right? Ionic particles are formula units, and covalent particles are molecules. When this happens, when our covalent bonds form, electrons are shared as pairs. Electrons are very needy when it comes to actually existing in an atom. They never like to go anywhere by themselves. They always like to be in pairs. So if you are sharing one pair, if you have one shared pair, that is called a single bond because it is a single pair of electrons. If you have 2 shared pairs, that is called a double bond. And if you have 3 shared pairs, that is called a triple bond. You're going to see single, double, and triple bonds pretty frequently in this unit. And they all have different properties. So a single covalent bond is going to be the longest bond. A triple bond is going to be the shortest bond, and a double bond will be sort of right in the middle. It'll have a medium length. And this makes sense if you think about your bonds as being sort of rubber bands holding two atoms together. So if you had a chlorine atom and a chlorine atom and they were bonded together, I will tell you they are connected by a single bond. So that's like having one single rubber band sort of holding these two things together. Versus nitrogen and nitrogen, this is connected by a triple bond. It's like having three rubber bands wrapping around these atoms and pulling them in together. So they're going to be pulled way closer because it's a much stronger bond. So your triple bonds are the shortest, they're pulled in the closest because the bond is strongest. On the flip side of that, our single rubber band, our single pair of electrons in our chlorine and our single bond, that's going to be the weakest. So it can't pull things in as close together, that's why it's the longest bond, and it's also the weakest, it's the easiest to break. And once again, your double bonds are right in the middle with a medium bond strength. Please note, I've drawn our bonds like rubber bands, but this is just a metaphor. Bonds happen between atoms, not around them. Bonds happen in the middle. All right, some properties of covalent bonds. These have a lower melting and boiling point, and they typically do not conduct electric current, just like we saw. So if you think for a second about why your covalent bonds have a lower melting and boiling point, means they're easier to break apart. And they're easier to break apart because they're not as attractive. Covalent bonds in general are weaker than ionic bonds when it comes to trying to separate them by heating. And that's because ionic bonds, that's when you have that positive and that negative together, right? Remember good old Coulomb's law? Opposites attract. When you have an actual positive and an actual negative holding each other together, that's really strong. This is harder to break. Versus covalent, they're just sort of, it's the power of friendship holding them together, which, while beautiful, is not quite as effective as this love story going on over here with our ionic bonds. So ionic is stronger, it's got the opposites attracting, versus covalent is sharing in the power of friendship. Not quite as strong, sorry. All right, a couple of examples here. Given the following Lewis structures for oxygen, fluorine, and nitrogen, why does it require more energy to break the bond between O2 than F2, right? It's harder to break this one than it is to break this one. And that comes down to the type of bond. This is a double bond. You see the two lines? It means it's a double bond. We're sharing two pairs of electrons here. Versus here, one line, one bond, one pair of electrons. Well, it's easier to separate one pair of electrons than it is to separate two pairs. So we can just say O2 double bond is stronger than the F2 single bond. That's really all you have to say about that. There are more electrons holding these together, more rubber bands. It's going to take more work to break this up than to break this up. All right, letter B says rank the following in order of increasing bond length. So shortest bond to longest bond. Shortest bond is going to be the strongest one, the one with the most electrons holding them together. That's going to be this guy. This is going to be the shortest bond because it's the strongest one. It's a triple bond. Then we have O2 is going to be a medium length because it's got a double bond, two pairs of electrons. F2 is going to be the longest bond. It's the weakest bond. It's got one pair of electrons holding it together. Pretty easy to break, and these are pretty spread apart. So that means that it's going to be N2, and then O2, and then F2. All right, next up in your book, you've got a fair amount of practice asking you about your different types of bonding, making you sort of think about how they all relate to each other. And the very last thing is a summary chart. And that's going to be really good practice to sort of synthesize all of the information from this video because you've learned a lot in this video. All right, so go ahead and work through those practice multiple choice questions. Those answers will be on the next slide. So pause the video when you're ready to check. Go ahead and unpause. All right, hopefully this is what you got for those first 10. And if you got all of these correct, then you've probably filled in your summary chart correctly as well. If you want to double check it, you can head over to my website, Check the Key. And if you're feeling good about this, it's time to move on to the next video, onto the quest, onto just doing some practice. So as always, good luck and happy studying.